Have you ever wondered why everything in the universe spins? From planets and stars to galaxies themselves? Right now, Earth is spinning at over 1,000 miles per hour, racing around the Sun at 93 million miles away, while our entire solar system speeds through the Milky Way at nearly 500,000 miles per hour. Yet we don't feel a thing. Our hearts beat normally. Our breath stays calm. It's as if we're perfectly still inside a universe that never stops moving. What if that stillness is an illusion? What if motion, not rest, is the true state of everything? If you enjoy the content, leave a like and subscribe to the channel to not miss any future content. In this video, we uncover why rotation might be the universe's oldest secret, one that began long before atoms, light, or even time itself. Prepare yourselves, we begin. Earth maintains rotational speeds exceeding 1,000 miles per hour, turning continuously beneath our position. Simultaneously, our planet rushes through its solar orbit at approximately 67,000 miles per hour. Currently, our entire solar system navigates the galactic plane at nearly 490,000 miles per hour. Strangely, we don't feel any of this motion. The water in your cup stays calm. The air doesn't feel like it's rushing past us. The stars above seem perfectly still. Yet this calmness is one of life's biggest illusions, a strange mix of constant motion and complete stillness. From tiny electrons to giant clusters of galaxies, everything in the universe spins or turns in some way. Atoms have rotating particles. Planets orbit around stars. Galaxies swirl into massive spirals of glowing stars and dust. Some scientists even think the entire universe might slowly rotate as part of its structure. But if everything is always moving, why do we feel like we're standing still? The answer lies in a simple but powerful idea called inertia. In the 1600s, Isaac Newton explained that objects keep moving unless something stops them. This principle is the reason Earth's non-stop spinning goes completely unnoticed by us. Humans travel alongside Earth rather than in opposition to it. Human bodies, surrounding atmosphere, oceanic masses, and terrestrial mountains all rotate collectively, synchronized within a singular, unbroken rhythm. Detecting motion requires differential experiences, mechanical forces, directional pulls, or state changes. Such variations remain absent in this scenario. Earth's rotation has stayed steady, smooth, and ancient for billions of years. The sky we see today looks almost the same as it did when early humans first gazed at the stars. Astronauts experience a similar feeling on a much larger scale. Even while orbiting Earth at 17,500 miles per hour and circling the planet every 90 minutes, everything inside their spacecraft feels calm. Without air resistance or friction, movement becomes impossible to feel. It feels just like being still. This effect is called uniform motion. The same principle lets you sip a drink on an airplane flying 500 miles per hour. Your cup, and the plane are all moving together. Only when turbulence causes sudden changes in motion do you actually feel it. Earth moves in the same smooth way, no shaking, no friction, no sudden shifts. Space is nearly a perfect vacuum, so nothing pushes back to let us sense our speed through the cosmos. As Neil deGrasse Tyson put it, we are living on a space rock orbiting a star that orbits a galaxy moving through the universe, and we call it home. It's a truth that's easy to overlook. Our senses simply weren't built to notice movement on such a grand scale. The balance system inside your inner ear helps you stay steady and sense motion, but it evolved for everyday movements like walking, running, or climbing, not for detecting the Earth's massive spin. Our inner ears respond to changes in speed, not steady motion. That's why you feel a car start or stop, but not while it's moving smoothly at a constant speed. Here on Earth, everything moves together with the planet. There's no sudden start or stop, just a constant, smooth glide through space. Scientists can still measure this hidden motion very precisely. One way is through the Foucault pendulum, first shown in 1851 by Léon Foucault. As it swings back and forth, the floor slowly turns beneath it, showing Earth's rotation without ever looking at the sky. In museums, people who watch these pendulums see time and motion blend together with every gentle swing. On a larger scale, Earth's spin is far from meaningless. It gives us day and night, helps maintain the planet's magnetic field, and protects us from harmful solar radiation. Without it, one side of Earth would burn under constant sunlight while the other froze in endless darkness. According to NASA's Goddard Space Flight Center, Earth's rotation is slowly slowing down. The moon's gravity tugs on our oceans, adding about 1.7 milliseconds to the length of each day every century. So even in our stillness, real change is always happening, slowly and quietly. Looking deeper, rotation isn't just an earthly feature. It's a cosmic signature. Stars are born when clouds of gas and dust collapse, and as they shrink, they spin faster, just like a figure skater pulling in their arms. Every planet, including Earth, carries this ancient spin. Our 24-hour day is a leftover trace of that original cosmic whirlpool. Even the sun rotates once every 27 days, stretching its magnetic field through space like glowing threads. And on an even grander scale, our Milky Way galaxy spins once every 230 million years, sweeping billions of stars, including our own, in a vast spiral dance that began long before Earth ever existed. The James Webb Space Telescope has captured galactic images so distant that their electromagnetic radiation has traveled for over 13 billion years. Even these primordial galaxies display rotational characteristics. ESA scientists studying these early formations detected subtle luminous variations. One side slightly redshifted, the opposite blue shifted, representing telltale rotational signatures. Apparently, the tendency toward rotation exists encoded within the universe's fundamental nature. How can universal rotation coexist with profound stillness? Partial explanation resides in relativity. According to Einstein, absolute motion lacks existence. Only relative motion between objects has meaning. From our terrestrial perspective, we occupy rest positions while the universe moves. From alternative reference frames, the opposite holds truth. This symmetry maintains physical consistency and renders our stillness an illusion of perspective. In deep space, astronauts aboard the International Space Station orbit Earth at nearly 5 miles per second, yet they feel weightless, not like they're moving at all. Their sense of down changes every 90 minutes as they circle the planet, but their minds quickly adapt. In the same way, we humans live as calm passengers on a planet that's constantly in motion. Our sense of stillness is actually a survival mechanism, a balance between what our senses can handle and what the universe demands. If we could truly feel Earth's spin, the sun's pull, and our galaxies drift through space, our sense of time and balance would fall apart. Motion and time are deeply connected. Earth's rotation gives us days and years, and that same rhythm shapes the heartbeat of the entire cosmos. Carl Sagan stated, "Time weaves into the universe's fundamental fabric, and we are the thread." The tranquility experienced presently represents not motion's absence, but the harmony of synchronized universal movement. When resting beneath the invisibly turning stars, remember, standing still is impossible. We glide through a cosmic river, gently, constantly, endlessly. Each stillness moment merely represents the universe moving too smoothly for detection. Within that perfect motion-calm balance, life discovers its quiet rhythm. We perpetually spin, always have. The silence perceived represents the sound of everything moving together. If we could somehow rewind time, not just by centuries or millennia, but all the way back to the very first second after the Big Bang, what would we see? Would there be light? Would we hear anything? Or would we witness only motion? A swirl, a twist, the first spin that set everything in existence into motion. The question of what started the universe's first rotation isn't just philosophical. It's a question of physics. The answer hides in the earliest fraction of time, when matter, energy, and space were just beginning to form. Scientists call this the Planck era, a moment so early, just 10 to the power of -43 seconds after the Big Bang, that our current understanding of physics breaks down. Even so, evidence hints at something fascinating. The universe might have been born spinning. When researchers studied the cosmic microwave background, the faint afterglow of the Big Bang recorded by satellites like NASA's WMAP and ESA's Planck, they found tiny temperature differences, just millionths of a degree apart. These small ripples show that the early universe wasn't perfectly smooth. Those tiny imperfections eventually grew into everything we see today: galaxies, stars, planets, and life itself. But scientists also noticed something even stranger: a faint, large-scale alignment in those ripples, as if the entire universe had a slight twist. They nicknamed it the axis of evil, a mysterious pattern suggesting the cosmos might have a preferred direction of rotation. According to data from WMAP and Planck, this could mean one of two things. Either it's just a quirk in how the data was measured, or it's real evidence that the universe itself once rotated. If that's true, that ancient spin may have shaped everything, from the spiraling arms of galaxies to the very flow of time itself. How could such rotation commence? The key might lie in quantum fluctuations, minute-random energy changes occurring when the universe measured smaller than atomic dimensions. Even in complete vacuum, these fluctuations happen naturally. As NASA's Goddard Space Flight Center describes, quantum fields never achieve perfect stillness. They continuously jitter. When the Big Bang occurred, those jitters underwent stretching and amplification by cosmic inflation. A brief but explosive expansion making the universe grow faster than light speed. That rapid stretching could have transformed some quantum jitters into swirling motions. The first cosmic spins. Inflation theory, proposed by physicist Alan Guth in 1981, explains why the universe appears smooth and uniform yet still contains structural seeds. Recent years brought data from Planck and Bicep 2 experiments suggesting that during inflation, subtle rotational modes known as B-modes may have existed in primordial gravitational waves. These tiny spacetime curls could represent the fossil record of the universe's first rotation, demonstrating that the Big Bang was not merely an explosion but a twisting birth imprinting spin across every matter scale. This makes sense when examining subsequent events. As the universe expanded and cooled, matter began forming. First quarks and gluons, then protons and neutrons, then atoms. Each carried minute angular momentum quantities. When gravity later gathered them into clouds and galaxies, that ancient angular momentum was conserved, the same principle making figure skaters spin faster by pulling in their arms. In physics, rotation cannot arise from nothing. Motion must originate from motion. Therefore, the first spin, however minimal, had to exist from the beginning. Astronomers today observe that rotation's fingerprints in distant galaxies. In 2011, researchers from the Harvard-Smithsonian Center for Astrophysics analyzed over 15,000 spiral galaxies and found subtle preferences in their rotation directions, an imbalance potentially tracing back to the early universe's spin. While not yet conclusive, This cosmic handedness hints that our universe may not be entirely random. A hidden rhythm might exist, a silent turn that everything still follows. Even dark matter, that invisible scaffolding holding galaxies together, could carry spin signatures. Computer simulations by NASA's Jet Propulsion Laboratory show that dark matter halos twist and rotate over billions of years, guiding the visible galaxies within them like whirlpools guiding leaves. Without that rotation, galaxies would disintegrate. The early universe seemingly set everything spinning, and even now, those motion echoes keep stars in balance. The origin question persists. Who or what began the spin? Physicists lean on one quiet answer: symmetry breaking. In the earliest fractions of a second, forces we now know as gravity, electromagnetism, and nuclear forces were once unified. As the universe cooled, they began separating. When that symmetry broke, tiny asymmetries, tiny imperfections, appeared. According to the European Space Agency, those imperfections are what allowed structure, motion, and spin to exist. In a perfectly balanced universe, nothing could move. In a slightly unbalanced one, it could dance. We observe this principle mirrored everywhere. In galactic rotation directions, in atomic rotational behavior, even in neutrinos' left-handed preference. Nature apparently isn't perfectly symmetrical, and that tiny flaw enables everything to turn. Some scientists have attempted detecting whether the entire universe rotates. In 2020, astrophysicist Lior Shamir from Kansas State University analyzed over 200,000 galaxies from the Sloan Digital Sky Survey. He found that galaxies in one sky half tend to rotate more in one direction than the other, suggesting large-scale cosmic spin. As Shamir wrote, "The universe may possess a collective motion pattern, a preferred direction that began in the early universe. This doesn't mean the cosmos spins like a top. Rather, space-time fabric itself might have twisted slightly during expansion. Even subtle twisting could cascade across billions of light years. To us, it feels invisible, but on universal scales, it could shape everything's geometry." NASA and ESA continue mapping the universe in increasing detail to test these theories. The James Webb Space Telescope already captures light from galaxies that formed just 300 million years after the Big Bang. Some of these ancient systems already show organized rotation, spiral patterns far too early in cosmic history to be explained by chance. This means spin seeds were planted almost immediately. The universe didn't have to learn rotation, it was born turning. Even on quantum levels, spin is fundamental. Every particle, electrons, protons, neutrons, carries intrinsic spin, a built-in matter property described by quantum mechanics. It's not physical spinning as we imagine, but a deeper mathematical rotation encoded in the wave function itself. As physicist Richard Feynman stated, "Spin is one of nature's most profound properties. The particle isn't literally spinning, it simply has spin as it has mass. Therefore, rotation wasn't added later. It was part of existence's blueprint. When observing the night sky, you witness that motion's inheritance. Every galactic swirl, every planetary orbit, every light photon descends from that first cosmic rotation. Without it, matter would never have clumped, stars would never have formed, and time itself would have no rhythm. Motion is not a universal accident, it is its heartbeat. Though we may never know exactly what triggered that first spin, evidence keeps whispering that it has always been there. Quiet, steady, invisible, yet written into everything observable. As ESA cosmologist Jan Tauber stated, "The universe carries memory not in words but in light patterns. Within those patterns lies the faint signature of the first motion, a twist older than time itself. When we ask who set the universe spinning, The most honest answer may be that the universe never learned to move. It was born already in motion. The spin wasn't created, it was inherited. The atoms in human bodies still turn with that first impulse. From the tiniest electron to the Milky Way's swirl, the same rotation continues, unbroken for nearly 13.8 billion years. We are not separate from that motion, we are its continuation. If rotation shaped the universe's birth, could it also be the reason life itself exists? Without rotation, Earth would be silent, no day, no night, no weather. Only a frozen hemisphere and a scorched one. A dead world drifting in light. Because it spins, this planet breathes. Every sunrise, every wave, every wind gust stems from the same ancient turn that began 4.5 billion years ago. Earth's spin is not just motion. It's an engine, a delicate balance sustaining everything we know as life. From the magnetic field shielding us from cosmic radiation to temperature cycles nurturing oceans and clouds, rotation shapes our world in both visible and invisible ways. According to NASA's Goddard Space Flight Center, our planet's rotational speed near the equator is about 1,037 miles per hour, completing one full spin every 23 hours, 56 minutes, and 4 seconds, what scientists call a sidereal day. This steady rhythm sets the pace for all biological and environmental cycles on Earth. Every plant, animal, and ocean current synchronizes to it, an invisible metronome ticking beneath everything alive. The first consequence of Earth's rotation is day-night alternation. It distributes sunlight across the surface, creating temperature gradients that drive wind, currents, and weather. Without that daily rotation, one hemisphere would roast under perpetual daylight while the other froze in eternal darkness. The boundary between them would be a violent storm wall, a lifeless twilight zone. Because Earth spins, the sun rises and sets, and energy is shared evenly enough to allow stable climates and habitable regions. Rotation also affects Earth's magnetic field, one of the most crucial shields for life. Deep beneath our feet, the planet's liquid iron core moves and churns, generating a magnetic dynamo. As NASA's magnetospheric multiscale mission describes it, Earth's magnetic field is created by molten iron motion within its core. This field deflects the solar wind, a stream of charged particles constantly emitted by the sun. Without it, those particles would strip away our atmosphere, much like what happened on Mars. The red planet spins once every 24.6 hours, almost like Earth. But its smaller, cooled core lost its molten motion long ago. Without a working magnetic field, its atmosphere was slowly eroded by the sun's radiation, leaving behind a dry, frozen desert. Here on Earth, the magnetic field also shapes the auroras, those soft glowing curtains of light near the poles. They are not just beautiful, they are proof of protection. Where magnetic lines bend and interact with charged solar particles, light is born. A reminder that our planet's rotation still powers an invisible force field around us. The spin's influence doesn't stop at shielding and sunlight. It also governs the atmosphere itself. Because Earth turns, air moving from the equator toward the poles curves, a phenomenon known as the Coriolis effect. This effect creates the vast spiraling systems of winds and currents that define our weather. It's why hurricanes spin, why jet streams flow, and why ocean gyres carry warm and cold water across the globe. Without the Coriolis effect, weather patterns would collapse into chaos, storms would not form, and climates would not balance. The rotation speed of a planet directly shapes its climate. NASA's Global Modeling and Assimilation Office, GMAO, has simulated exoplanets with slower or faster spins. Slower rotation causes one side to overheat and the other to freeze, while faster rotation can generate extreme winds and shorter days that disrupt atmospheric stability. Earth's 24-hour rhythm is almost perfect, long enough to distribute energy evenly, but short enough to prevent overheating. The length of day also affects biology. Living organisms evolved internal clocks, circadian rhythms, that align with the planet's rotation. According to research published by the National Center for Biotechnology Information, NCBI, every living cell on Earth carries a molecular timekeeper that syncs to this 24-hour cycle. This rhythm regulates when plants open their leaves, when birds migrate, and even when humans sleep. If Earth stopped rotating, this biological harmony would shatter. Light and dark would no longer alternate regularly, and life as we know it could not adapt. Rotation also shaped how the moon became our companion. Billions of years ago, a Mars-sized object called Theia collided with the young Earth. The impact sent debris into orbit, which later coalesced into the moon. The collision also increased Earth's spin dramatically. Over time, the moon's gravity has been slowing that spin, gradually lengthening our days from about 6 hours to the current 24-hour cycle. Tidal forces between the two bodies keep the planet's axial tilt stable, preventing extreme climate swings. ESA's Gaia mission confirms that this stability is essential for long-term habitability. Planets that wobble too much often experience catastrophic climate variations. The Moon and Earth now exist in a slow gravitational embrace. The same tides that shape our oceans also slow our rotation by about 1.7 milliseconds per century, as recorded by NASA's Jet Propulsion Laboratory. It's a reminder that even the length of our day, the heartbeat of our world, is gradually changing, one imperceptible moment at a time. Looking beyond our planet, we find that rotation plays a similar role in other worlds. Jupiter, for example, spins once every 9 hours and 56 minutes, making it the fastest rotating planet in the solar system. Its speed drives ferocious jet streams and storms, including the Great Red Spot, a hurricane larger than Earth that has raged for centuries. Rotation there creates chaos yet also stability, distributing heat and shaping the planet's banded beauty. Meanwhile, Venus, which rotates backward and extremely slowly, one full rotation every 243 Earth days, has almost no magnetic field. Its thick carbon dioxide atmosphere traps heat in a runaway greenhouse effect, making it the hottest planet in the solar system. The comparison is striking. Too fast and storms dominate. Too slow and protection disappears. Even Mars, with a day just 40 minutes longer than ours, shows what happens when internal motion fades. As its core cooled, its once strong magnetic field vanished, allowing solar radiation to strip away its air and water. The faint remnants of magnetism still linger in the crust, ghostly traces of a spin that once sustained a dynamic world. Rotation, then, is not optional for habitability, it's fundamental. In 2023, scientists using the James Webb Space Telescope observed exoplanets like WASP-39b and TRAPPIST-1e, discovering that those with measurable spin or atmospheric circulation show clearer signs of chemical balance and temperature distribution. Without rotation, energy remains trapped or lost, creating unstable environments. As NASA's Exoplanet Exploration Program summarizes, rotation plays a critical role in determining the climate and potential habitability of a planet. Rotation may also be tied to magnetic protection on distant worlds. A 2021 study by the Harvard-Smithsonian Center for Astrophysics noted that exoplanets with rapid spins tend to maintain molten metallic cores longer, extending the life of their magnetic fields. Those fields, in turn, shield atmospheres and may increase the likelihood of surface liquid water, the essential ingredient of life. So when we ask if spinning made life possible, the data says yes. Rotation shapes everything from a planet's day length to its temperature gradients, atmosphere, weather, and magnetic safety. Life, it seems, thrives not despite motion, but because of it. Our world's rotation speed has changed over eons, yet its effects continue to echo across time. It controls the rhythm of tides, the growth of forests, the migrations of animals. It defines our sense of time itself, not as an abstract idea, but as the physical turning of the world beneath us. As astrophysicist Neil deGrasse Tyson stated, "We are not just in the universe, we are of the universe. The Earth turns, and so do we." Every rotation carries the whisper of 4.5 billion years of balance and motion. If Earth stopped spinning tomorrow, the oceans would surge toward the poles, the atmosphere would collapse into chaos, and the planet would lose its breath. But tonight, as it spins gently beneath you, everything still works perfectly, quietly, continuously. Perhaps it's no exaggeration to say that the rotation of Earth is the quiet architect of life. The same cosmic motion that once swirled dust into a planet now spins that planet into morning, into wind, into rain, into us. Beyond a certain speed, rotation doesn't just move matter, it can start to twist time itself. When rotation reaches its limit, it stops being motion and becomes distortion. At extreme speeds, turning objects no longer just move through space. They begin to pull at time itself. Einstein's general theory of relativity, published in 1915, predicted that gravity and motion are inseparable, two expressions of how mass curves spacetime. The greater the energy or spin of an object, the more it twists the geometry around it. This twisting of spacetime by rotation is called frame dragging, and it's one of the most subtle, beautiful, and verified predictions of modern physics. Imagine spacetime as a calm lake. When a massive object spins, like Earth or a black hole, it stirs that lake, creating tiny vortices in the very flow of time. In those whirlpools, the direction of time itself can begin to curve. NASA physicist Francis Everett, who led the gravity probe B experiment, described it like this: "As the Earth rotates, it drags spacetime around with it, much like a spinning sphere twisting honey in which it is immersed." Gravity Probe B, launched in 2004, used 4 ultra-precise gyroscopes orbiting 400 miles above Earth to measure this effect. After a year of observation, NASA confirmed that our planet's rotation drags spacetime by about 0.000011 degrees per year. That may sound small, but it matches Einstein's equations with extraordinary precision. Even our gentle planet, spinning once every 24 hours, is capable of bending the flow of time. Now, imagine rotation billions of times faster and gravitational fields billions of times stronger. That's what happens near a neutron star. When a massive star dies, it collapses under its own gravity, squeezing matter so tightly that protons and electrons merge into neutrons. The result is an object only about 12 miles wide, but with mass greater than that of our Sun. To conserve angular momentum, these stars spin unimaginably fast, up to 700 times per second. Astronomers call them pulsars because their magnetic poles emit radiation beams that sweep across space like cosmic lighthouses. As they rotate, they create the strongest known magnetic fields in the universe and twist spacetime so violently that even light struggles to travel in straight lines. NASA's NICER instrument aboard the International Space Station has mapped these distortions, showing that time near a pulsar ticks more slowly than it does on Earth. The stronger the spin, the slower the clock. Einstein's equations tell us that this isn't magic. It's gravitational time dilation. Time runs more slowly in regions of stronger gravity or faster motion. When you're near a massive spinning body, space-time itself is pulled into its rotation. You can't stay still, you're dragged along as if the universe itself is rotating you. This phenomenon is especially extreme near Kerr black holes that spin. Named after mathematician Roy Kerr, who first solved Einstein's equations for a rotating black hole in 1963. A Kerr black hole is perhaps the most exotic structure we know. Unlike a simple non-rotating black hole, which merely pulls everything inward, a Kerr black hole spins spacetime around its axis. Close enough to the event horizon, the speed of that rotation approaches the speed of light. Nothing, not even time, can resist being dragged along. The region outside the event horizon where this frame dragging occurs is called the ergosphere. Within it, nothing can remain stationary relative to distant space. Every particle, every photon must rotate with the black hole. It's as if space itself becomes liquid, spinning in a vast, invisible whirlpool. In 2021, using NASA's Chandra X-ray Observatory, scientists observed matter spiraling around a black hole at the center of galaxy M87, confirming that it rotates near the limit predicted by relativity. Inside that whirlpool, time behaves differently. If you could hover safely near the ergosphere, an impossible feat for now, your clock would tick slower than those on Earth. For every minute you experience, hours could pass for the rest of the universe. Einstein wrote, "Time and space are modes by which we think, not conditions in which we live." ESA's Event Horizon Telescope, HT, captured the first ever image of a black hole's shadow in 2019 and later, in 2022, released the image of Sagittarius A*, the supermassive black hole at the center of our galaxy. The luminous ring we see is not light from the black hole itself but from matter spiraling around it, light bent and delayed by spacetime curvature. Those glowing arcs are visual proof that rotation and gravity together can bend not just light but the flow of time. The same laws apply on smaller scales too. Even satellites orbiting Earth experience tiny time differences. The global positioning system must constantly correct for both gravitational and velocity-induced time dilation. If left unadjusted, GPS clocks would drift by 38 microseconds per day, enough to cause navigation errors of several miles. So even here, where space-time seems calm, the bending of time is not theory, it's part of daily life. When astrophysicists simulate regions near a Kerr black hole, the mathematics becomes breathtaking. Rotation can twist space-time so sharply that closed time-like curves appear paths where a particle could, in theory, loop back to an earlier point in time. Whether these loops are physically real remains uncertain, but they emerge naturally from Einstein's equations. In these extreme environments, past and future lose their fixed meaning. The James Webb Space Telescope, with its infrared precision, now observes the accretion disks of distant quasars galaxies powered by supermassive rotating black holes. JWST's spectra show light from these disks stretched and redshifted, a sign that time runs slower in those regions. Some of the light we detect today left those spinning giants over 13 billion years ago, meaning we're watching time itself stretched across the cosmos. Rotation, it turns out, doesn't just shape matter, it defines how time flows near it. The faster and denser the spin, the greater the warping of space-time. From our gentle planet to the violent hearts of galaxies, the universe uses spin to sculpt both motion and time. What we call now is different everywhere, depending on how fast and how deep the local space-time is turning. Even light, which normally travels at the universe's ultimate speed limit, is forced to bend and slow near rotating masses. NASA's New Star and XMM Newton missions have captured X-ray echoes around black holes' light trapped briefly in rotation before escaping. In these echoes, time stretches like a soft thread, measurable, predictable, yet endlessly strange. One might wonder whether the universe itself is twisting time on a grand scale. Large-scale cosmic rotation could subtly influence how time flows across billions of light-years. While current cosmological data from ESA's Planck satellite show no strong evidence for universal spin, the question remains open. Even the faintest twist over cosmic distances might leave fingerprints in the polarization of ancient light, hints that time itself has a preferred direction. As physicist Kip Thorne, co-author of The Science of Interstellar, explained, "In the warped space-time near a spinning black hole, the future of one observer can become the past of another. Rotation doesn't just bend trajectories. It bends the sequence of events, the very rhythm of existence. And yet, for all its strangeness, the effect is consistent and measurable. Time dilation around rotating bodies has been verified by atomic clocks aboard aircraft, satellites, and in mountain laboratories. The faster you move or the deeper you fall into gravity, the slower your time flows. It's not an illusion. It's the universe keeping perfect balance. Yes, rotation can bend time, but what's even more intriguing is why that bending seems to follow a pattern. A smooth universal law that links motion, gravity, and energy into one continuum. From Einstein's equations to every ticking satellite, it all points to one truth. The universe doesn't just move through time, it creates it through motion. Currently, our own sense of time is tied to Earth's gentle spin. The sun's pull, the galaxies turn. We are surrounded by motion so precise it writes the seconds we live in. If rotation can bend time, what happens when time starts to control the spin? Every second we live is shaped by motion. The ticking of watches, the pulse of atomic clocks, even heartbeat rhythms, all depend on something spinning. Electrons rotate inside atoms. Earth turns once every 24 hours, and as it spins, it drags space-time just enough to change how time flows. At the equator, where Earth's surface moves fastest, about 1,037 miles per hour, clocks run slightly slower than those at the poles. It's not because of temperature or air pressure. It's because of relativity. Einstein's theory showed that motion and gravity can stretch or compress time depending on how fast and how deep you are in a gravitational field. So yes, spin controls time. But the question remains, who or what controls spin? To answer that, scientists look at the most reliable timekeepers humanity has ever built: atomic clocks. Inside them, electrons whirl around atomic nuclei at fixed energy levels. When they jump between those levels, they release photons at an exact frequency. That frequency, defined by the cesium-133 atom, sets the length of 1 second, 9,192,631,770 cycles of radiation, corresponding to the transition between two hyperfine levels of the ground state of cesium-133. Those words, established by the International Bureau of Weights and Measures, describe how every second of our lives is calibrated to a tiny atomic spin. The rotation of electrons inside atoms is a kind of quantum spin, not physical twirling, but a fundamental property of matter. In quantum mechanics, particles carry spin values that determine how they behave in magnetic fields, how they bond, and even how they obey the Pauli exclusion principle, the rule that no two electrons can occupy the same quantum state. At its smallest scale, timekeeping depends on spin, not the turning of a planet, but the internal angular momentum of atoms themselves. Just as atomic spins govern time inside our laboratories, planetary spins govern time on cosmic levels. Earth's rotation defines the length of a day, while its orbit around the sun defines the length of a year. These motions aren't fixed, they slowly drift. Tidal forces from the moon are gradually slowing Earth's spin, adding 1.7 milliseconds per century to each day. To keep atomic time and planetary time synchronized, scientists use a system called leap seconds. Occasionally, the world's atomic clocks are adjusted by 1 second to align with the planet's natural rotation. In a sense, we're constantly recalibrating human time to match Earth's cosmic spin. If you compare clocks at different latitudes, the differences are measurable. A clock placed at sea level near the equator, moving fastest due to Earth's spin, runs slightly slower than one placed high in the mountains or near the poles. This is both special and general relativity at work. As NASA explains, a clock on the equator ticks more slowly than one at the poles because it's moving faster and deeper in Earth's gravitational potential. The difference is tiny, a few nanoseconds per day, but real. Our phone's GPS systems must correct for this effect constantly. Each of the 24 GPS satellites orbits Earth at about 8,700 miles per hour, 12,500 miles above the surface. In orbit, they experience weaker gravity and higher speed, causing their onboard atomic clocks to run faster by about 38 microseconds per day. If uncorrected, this would make navigation errors of several miles accumulate every few hours. To keep time consistent, engineers combine Einstein's equations with real-world measurements, literally adjusting for the curvature of spacetime caused by Earth's rotation. Every time we check a map or receive a location signal, we're witnessing relativity in action, a quiet collaboration between gravity, motion, and spin. But who started the spin in the first place? Astronomers trace it back to angular momentum, a conserved quantity in physics. When the solar system formed 4.6 billion years ago, a cloud of gas and dust collapsed under gravity. As it shrank, it spun faster, just like a skater pulling in her arms. That primordial motion distributed angular momentum to everything inside. The sun, the planets, their moons. Each body still carries a portion of that ancient rotation. No external force continually keeps them spinning. They continue because of inertia, the same law that keeps a planet in motion until something resists it. In space, where friction is nearly absent, spins can last for billions of years. So the answer to who controls spin is no one. Once set in motion, the universe needs no hand to keep turning. The relationship between spin and time grows stranger the deeper we look. Inside atoms, spin determines energy states. On planetary scales, spin defines days. On cosmic scales, spin drags time itself. And all these levels are connected by one law: angular momentum is conserved. Time, in that sense, is not an independent entity, it's a reflection of how energy and spin interact. In 2016, ESA's Gaia mission mapped the precise motions of over 1 billion stars in the Milky Way. The data revealed that our entire galaxy rotates once every 230 million years, carrying the Sun and its planets along in a vast spiral. Each star's orbit contributes to a grand cosmic timepiece, one rotation marking the rhythm of galactic time. Just as atomic spin defines seconds, stellar spin defines eons. Even the Sun spins once every 27 days at its equator, but not uniformly. The poles rotate slower, a phenomenon called differential rotation. This twisting motion generates magnetic fields that shape solar flares and coronal mass ejections. When those magnetic storms reach Earth, they distort our own magnetic field and can even affect satellites and power grids. From the atomic scale to the solar scale, spin is not passive. It sculpts fields, defines rhythms, and interacts with the very tools we use to measure time. Einstein's relativity linked these patterns beautifully. In his equations, the geometry of spacetime depends on energy and momentum, including angular momentum. In other words, spin curves time. If you remove spin, spacetime becomes simpler, flatter, less dynamic. Add spin and it warps, gently for planets, violently for black holes. We might say that time itself is recorded in motion. The second is written in atomic spin, the day in planetary spin, the cosmic epoch in galactic spin. Everything that moves measures time, and everything that measures time moves. In 2022, the James Webb Space Telescope observed distant galaxies whose light has traveled over 13 billion years. Even in those primordial galaxies, astronomers detected rotation, a sign that angular momentum existed almost immediately after the Big Bang. That means the law connecting spin and time has been in operation since the universe's earliest seconds. Spin is not a product of time, it's part of what gives time its flow. If spin governs time and spin itself arises naturally from the conservation of motion, then who or what controls it? The most precise answer science can offer is, the universe controls itself. Every spin is balanced by another. Every slowing motion is matched by an exchange of momentum elsewhere. Even the smallest quantum particle obeys these same equations, ensuring that angular momentum remains perfectly conserved across space and time. NASA's Jet Propulsion Laboratory put it simply, the laws of motion don't change. The universe runs on balance. What is lost in one place is gained in another. There's no master clock, no hidden hand. The very act of motion maintains its own timing. Spin, then, is the universe's internal gyroscope, its built-in way of keeping everything aligned. From our atoms to the stars above, the same principle governs every scale. Even when systems decay, collide, or slow down, their angular momentum transfers onward, keeping the cosmic clock ticking. When you ask who controls the spin, the universe gently answers, no one must. Motion is self-sustaining. It is the quiet balance that underlies both time and existence. The atoms within us spin in harmony with the turning Earth, the orbiting moon, the spiraling galaxy. We are already part of that motion. Every heartbeat a fraction of a universal rhythm that began long before clocks, calendars, or light itself. As that rhythm continues, another question slowly rises, not about motion, but about something that stretches beyond it into the structure of the cosmos itself. If the universe depends on perfect balance, what happens when that symmetry breaks? If everything had once been perfectly balanced, nothing would ever have moved. No stars, no atoms, no time, only stillness, endless and unchanging. But the universe we know began not with perfection but with a tiny imperfection. A small crack in symmetry that allowed everything to unfold. In physics, symmetry means that the laws of nature behave the same way in every direction, at every point, and for every observer. When symmetry holds perfectly, nothing has a reason to change. But when it breaks, even slightly, motion appears, structure emerges, and time gains direction. As NASA's Goddard Space Flight Center describes it, the universe exists as we know it because perfect symmetry didn't last. Let's drift back to the first fractions of a second after the Big Bang. According to the standard model of particle physics, the early universe was a hot, dense plasma where the four fundamental forces, gravity, electromagnetism, and the strong and weak nuclear forces, were once unified. But as the universe expanded and cooled, these forces began to separate. This process, called spontaneous symmetry breaking, shaped everything from the structure of atoms to the fabric of spacetime itself. ESA's Planck mission mapped the cosmic microwave background, the faint afterglow of the Big Bang, and found it was astonishingly uniform, yet not perfect. Tiny variations in temperature, only 1 part in 100,000, reveal the first signs of broken symmetry. Those minute differences in energy density later grew into galaxies, stars, and planets. Without those fluctuations, the universe would remain smooth and static, an endless, featureless mist. Even matter itself owes its existence to broken symmetry. When the universe was young, it created matter and antimatter in nearly equal amounts. But nearly is the key. For every billion particles of antimatter, there were 1,000,000,001 of matter. That slight imbalance, known as baryon asymmetry, meant that when matter and antimatter annihilated each other, a tiny fraction of matter survived. That leftover matter became the stars, the planets, and everything we see today. In 1964, physicists James Cronin and Val Fitch discovered this subtle asymmetry in particle behavior, an effect now called CP violation. Their experiment with neutral kaons showed that the laws of physics treat matter and antimatter slightly differently. This discovery earned them the Nobel Prize and provided the first clue that the universe prefers one direction, one spin, one imbalance. As ESA's particle physics division notes, without CP violation, the universe would contain no matter, only light. In a way, imperfection made everything possible. The mechanism behind this imbalance is still being studied. At CERN, the Large Hadron Collider investigates particles like the Higgs boson, which plays a crucial role in breaking electroweak symmetry. When the universe cooled below a critical temperature, about 10 to the power of -12 seconds after the Big Bang, the Higgs field gained a non-zero value everywhere in space. That field gives particles mass and breaks the symmetry between light and matter. It's often said that the Higgs field is what froze the universe into its current form, locking in the differences that made complexity possible. But not all symmetry breaking is violent. Sometimes it's gentle, like the way a perfectly balanced pencil will eventually fall in one direction. The universe may have chosen a direction for time in a similar way. In the earliest instance, time could have flowed equally forward or backward, but a tiny fluctuation, perhaps in entropy, perhaps in quantum probability, pushed it forward, setting the arrow of time. As physicist Sean Carroll wrote, "The arrow of time is the result of low entropy at the beginning of the universe, a state of broken symmetry that all later moments remember. When we measure time, we're really measuring how far we've drifted from perfect symmetry. Even the cosmic web, the vast structure of filaments connecting galaxies, arises from this imbalance. JWST's deep field images show galaxies forming along invisible threads of dark matter that trace the earliest quantum fluctuations in density. Those fluctuations began as random variations magnified by cosmic inflation just moments after the Big Bang. What began as tiny irregularities became the architecture of the universe. Without asymmetry, gravity itself could not work the way it does. A perfectly uniform distribution of matter would pull equally in all directions, producing no motion. But with slight unevenness, gravity could act, drawing matter into clusters, forming galaxies, stars, and eventually planets. NASA's WMAP mission described it simply: if the early universe had been perfectly smooth, no structure could have formed, no galaxies, no stars, no life. Even at the quantum level, particles betray the same imbalance. Neutrinos, for instance, are known to have chirality. They all spin in the same left-handed direction. This handedness of the universe may be another echo of the original symmetry breaking. It's a pattern that repeats from the tiniest scales to the largest, from subatomic spins to galactic rotations. Everywhere we look, the universe shows preference. Galaxies rotate clockwise or counterclockwise in unequal numbers. Molecules of life like amino acids and sugars have handedness too, a bias called chirality that underlies all biology. Though life arose billions of years after the Big Bang, its chemistry still reflects the same ancient asymmetry written into the fabric of the cosmos. This connection between cosmic imbalance and biological structure fascinates scientists. A 2020 study by NASA's Astrobiology Institute suggested that polarized ultraviolet light from early stars may have destroyed right-handed amino acids, leaving left-handed ones to dominate on Earth. If true, then even life's molecular spin owes its direction to the universe's first broken symmetry. Perhaps the most elegant demonstration of this principle lies in the cosmic microwave background's polarization. The Planck satellite detected tiny swirls, B-mode polarization, that may hint at primordial gravitational waves. These waves would be the fingerprints of inflation, the universe's first, fastest spin, and the moment when symmetry gave way to motion. If confirmed, they would be direct evidence that the universe's very first act was to break perfect balance. From the way light bends to the way galaxies align, everything we measure points back to that single principle. Imperfection drives creation. Symmetry is elegant but fragile. Break it slightly, and the universe wakes up. As theoretical physicist Murray Gell-Mann stated, if the world were perfectly symmetrical, there would be nothing. It's the deviations, the slight differences in energy, in motion, in charge that make reality possible. When we observe the universe through telescopes like JWST, what we're really seeing is the fossil record of broken symmetry, the first flicker of imbalance that became time, structure, and light. From that faint imperfection, everything else followed. Galaxies, planets, oceans, and the quiet rotating world beneath our feet. Human beings are living proof of asymmetry. We are made from matter that once outnumbered its mirror twin by just 1 in a billion. Every atom in our bodies carries the trace of that cosmic bias, preserved since the first microseconds of existence. The universe began because symmetry broke. Perfection gave way to motion, and motion gave rise to time. A small crack in balance created everything that would ever spin, shine, or breathe. As we follow that first imbalance outward, we reach a new puzzle, a question not about beginnings, but about what keeps the cosmos together despite its restless motion. Because if galaxies spin faster than they should, something invisible must be holding them in place. Galaxies spin at impossible speeds. Stars on their outer edges move so fast that by all laws of physics they should fly apart, scattered like sparks from a turning wheel. And yet they don't. Something unseen is holding them in place, a silent mass that outweighs everything we can see. Astronomers call it dark matter. It doesn't shine, reflect, or absorb light. It doesn't collide, melt, or form atoms, but it gravitates, pulls. And that invisible pull keeps entire galaxies from tearing themselves apart. The mystery began in the 1930s when Swiss astrophysicist Fritz Zwicky studied the Coma cluster, a vast collection of more than 1,000 galaxies drifting 320 million light-years away. Zwicky measured how fast the galaxies were moving and found that their visible mass, the stars, gas, and dust, wasn't nearly enough to hold them together. The cluster should have flung itself apart long ago. He proposed something shocking. An unseen mass must be there, providing the missing gravity. He called it Dunkel Materie, dark matter. For decades, his idea remained a whisper, until the 1970s, when American astronomer Vera Rubin began measuring the rotation curves of spiral galaxies using data from the Kitt Peak National Observatory in Arizona. Rubin found that stars far from galactic centers were orbiting just as fast as those near the core, a discovery that defied Newtonian physics. According to gravity alone, orbital speeds should drop as you move outward, just as planets far from the sun move slower. But Rubin's graphs were flat. Every star, from the center to the edge, moved at nearly the same speed. Something unseen was supplying extra gravity across the galaxy. As NASA later summarized, The rotation curves of galaxies tell us there's much more mass than meets the eye. That mass, dark matter, now appears to make up about 85% of all matter in the universe, roughly 5 times more than the visible matter that makes up stars, planets, and people. Scientists estimate that galaxies sit inside vast dark matter halos, invisible spheres extending far beyond their visible edges. Each halo acts as scaffolding, binding stars and gas together through gravity. Without it, galaxies like the Milky Way would unravel in a few million years. Simulations from NASA's Goddard Space Flight Center show that dark matter provides the cosmic glue that allows galaxies to form, merge, and persist. The European Space Agency, ESA, has also long observed this invisible structure through gravitational lensing, the bending of light by massive objects. When light from distant galaxies passes near a cluster filled with dark matter, the unseen mass warps spacetime, magnifying and distorting the background light into graceful arcs. ESA's Euclid mission, launched in 2023, is designed to map this effect across billions of galaxies, creating the most detailed 3D chart of dark matter ever made. Even before Euclid, the Hubble Space Telescope gave us stunning glimpses of this cosmic lensing. In 2006, Hubble captured the Bullet Cluster, where 2 galaxy clusters had collided. X-ray images from NASA's Chandra Observatory showed that the hot gas, ordinary matter, lagged behind after the collision. But when scientists mapped the total mass using gravitational lensing, the bulk of it lay ahead, separated from the visible matter. It was clear proof that most of the mass was invisible, an independent, unseen component of the universe. Dark matter does not interact with light or electromagnetic forces, which is why it cannot be seen directly. It interacts only through gravity and possibly the weak nuclear force. The leading candidates are hypothetical particles such as WIMPs, weakly interacting massive particles, or axions, both predicted by extensions of the Standard Model of Physics. Experiments like XENONNT in Italy and LUX Zeppelin in South Dakota are trying to detect these particles through rare collisions with atomic nuclei. So far, no confirmed detection has been made, but the search continues quietly, deep underground, shielded from cosmic rays. Meanwhile, NASA's Fermi Gamma Ray Space Telescope has searched for subtle signatures of dark matter annihilation in the centers of galaxies. And JWST has begun observing the faint structures of galaxies in the early universe, less than 400 million years after the Big Bang. Even at that young age, galaxies already showed stable rotation, suggesting that dark matter halos were already in place. ESA scientists wrote, "Dark matter must have formed early, shaping the universe long before the first stars ignited. On cosmic scales, dark matter determines not only how galaxies spin, but how the universe evolves." Computer simulations like NASA's Illustris and Eagle projects show that without dark matter, galaxies would never form. Matter would remain evenly spread, unable to clump together under gravity. Dark matter provided the invisible scaffolding upon which visible matter condensed. As astrophysicist Neil deGrasse Tyson put it, "It is the greatest cosmic mystery of our time, a shadow universe holding ours in its grip. Though invisible, dark matter leaves a trail everywhere. It shapes galaxy clusters, influences cosmic filaments, and even affects the way the universe expands. Dark matter doesn't emit radiation, but its gravity slows the outward expansion that began with the Big Bang. This cosmic tug-of-war between dark matter's gravity and dark energy's acceleration defines the large-scale structure of everything. How fast are galaxies really spinning? Take our Milky Way. The Sun orbits the galactic center at about 514,000 miles per hour, completing one rotation every 230 million years. At that speed, and given the visible mass we can account for, our galaxy should have torn itself apart long ago. But the dark matter halo surrounding it, extending perhaps 200,000 light-years beyond the visible disk, adds the necessary mass to keep it whole. This balance between spin and gravity is delicate. If dark matter were just slightly less abundant, galaxies would scatter. If slightly more, they'd collapse under their own weight. ESA's Planck satellite estimates the universe's composition as 68% dark energy, 27% dark matter, and only 5% ordinary matter. Everything we can see, every star, planet, and person, accounts for just 1/20th of what actually exists. What makes dark matter so puzzling is that it does not fit neatly into our known physics. We can measure its gravitational pull, map its distribution, and simulate its effects, but we cannot yet identify what it is. Some physicists even suggest that our understanding of gravity itself might need revision. Modified theories like MOND, modified Newtonian dynamics, and Tevis attempt to explain galaxy rotation without dark matter. But so far, dark matter remains the simpler, more consistent explanation. New missions aim to solve this enigma. ESA's Euclid and NASA's Nancy Grace Roman Space Telescope will work together to map billions of galaxies and measure how dark matter has shaped their growth over 13 billion years. Their goal is not only to understand dark matter, but also to reveal how it interacts, or doesn't, with dark energy, the mysterious force driving the universe's expansion. Even the James Webb Space Telescope contributes to this quest. By observing the earliest galaxies, JWST allows scientists to test whether dark matter behaves the same way across cosmic time. If the formation of those early systems matches current models, it strengthens the case that dark matter's invisible hand has always been at work. It's strange to think that what keeps galaxies whole is something we cannot see or touch. Yet its gravitational melody holds the cosmos in tune. Without it, the universe would lose its shape, its stars flung into darkness, its clusters unbound. Dark matter is the quiet architecture of existence, a framework made not of light, but of stability. Every star we've ever seen, every galaxy that drifts across our telescopes, is balanced upon something invisible. We are living in a universe held together by shadows, forces that act without being seen, guiding the motion of everything that spins. As we trace that invisible hand through the darkness, we begin to notice something even stranger. If dark matter holds galaxies together, could it also have shaped the direction of life itself, even down to the spin of molecules? Every living thing on Earth is twisted just slightly. Our DNA spirals to the right. The amino acids that build every cell in our bodies bend to the left. This one-sidedness, called chirality, is one of the deepest mysteries in biology. It means that life, down to its smallest molecular shape, has a preferred direction, a bias, a spin. In chemistry, chirality means handedness. Just like our left and right hands are mirror images that can't be perfectly aligned, certain molecules exist in two forms, one left-handed and one right-handed. In most chemical reactions, both versions can form equally. But in living organisms, only one hand is ever chosen. DNA and RNA always twist to the right. Amino acids, which form proteins, always twist to the left. It's as if long ago, life made a permanent decision and has followed that spin ever since. Scientists have spent decades trying to understand why. If chemistry alone can produce both directions equally, then something outside of biology must have nudged life toward one side. One possible clue comes from the light of ancient stars. Light waves can be polarized, meaning they oscillate more strongly in one direction than another. In the early universe, young, massive stars emitted intense ultraviolet radiation that became circularly polarized as it scattered through magnetic dust clouds. According to studies conducted by NASA's Astrobiology Institute and Ames Research Center, this polarized light could selectively destroy one type of amino acid more than the other. Over millions of years, that subtle preference may have seeded the handedness of life itself. The European Space Agency's Rosetta mission added evidence to this theory. When Rosetta's Philae lander touched down on Comet 67P/Churyumov-Gerasimenko in 2014, it detected complex organic molecules, including amino acid precursors. Analysis of their structure showed signs of asymmetry, hinting that chiral bias may have existed before life began on Earth. That means the direction of life's molecules could have been inherited from interstellar chemistry, shaped by cosmic light and motion long before our planet even formed. Another clue comes from meteorites. In 1969, the Murchison meteorite fell in Australia. It contained more than 70 different amino acids, and scientists later discovered a slight excess of left-handed forms. As NASA's Johnson Space Center explained, the Murchison meteorite preserves chemical fingerprints from before the solar system formed. Those fingerprints show that the universe already had a preferred molecular direction, one that life would later adopt. Why left for amino acids and right for DNA? It might be more than coincidence. Some researchers believe the opposite orientations actually complement each other, one determining structure, the other stability. Left-handed amino acids fold proteins that can bond perfectly with right-handed nucleic acids, forming the biochemical harmony that sustains life. Reverse that orientation, and the chemistry simply doesn't work as efficiently. Still, this asymmetry didn't emerge randomly. It may trace back to the earliest quantum imbalances, fluctuations in energy and spin that occurred within microseconds after the Big Bang. Experiments at CERN and Fermilab have confirmed that some subatomic particles, such as neutrinos, always spin in a left-handed direction. This universal handedness or parity violation shows that even fundamental physics isn't perfectly symmetrical. In 1956, physicists Qian-Xiong Wu and Tsungdao Li proved this through their historic beta decay experiment. They showed that the weak nuclear force, one of the four fundamental forces, does not treat left and right equally. As Wu herself described, nature is not as symmetrical as it appears. If even the universe's basic forces favor one spin over another, then it's not hard to imagine that life's molecules too inherited this cosmic preference. On Earth, this pattern continues everywhere we look. From the swirling arms of hurricanes to the spiraling growth of shells, spin and asymmetry are built into nature's design. The Coriolis effect, caused by Earth's rotation, determines the direction of large-scale storms. Counterclockwise in the northern hemisphere, clockwise in the southern. Even our planet's magnetic field has a defined polarity, flipping occasionally but never losing its sense of direction. The farther we look into space, the more this cosmic bias reappears. In 2011, astronomer Lior Shamir analyzed tens of thousands of galaxies using data from the Sloan Digital Sky Survey. He found a small but significant difference in the number of galaxies rotating clockwise versus counterclockwise. That imbalance suggested a large-scale directional pattern, perhaps a relic of the universe's early spin. If true, then the same asymmetry that governs galaxies may echo all the way down to the molecular structures of life. This connection between cosmic motion and biochemistry has fascinated scientists for decades. A 2021 study from the Tokyo Institute of Technology simulated the effects of circularly polarized light on amino acids in interstellar environments. They found that even a small imbalance in photon spin could lead to a measurable difference in molecular chirality. In other words, Light shaped by cosmic rotation might have literally set the direction of life. It's easy to forget that light itself carries spin. Photons can have right-handed or left-handed polarization, a kind of angular momentum that affects how they interact with matter. When early starlight passed through magnetic fields twisted by rotation, that spin could imprint a bias onto the molecules it touched. Even the simplest dust grains floating between stars might have been polarized by galactic motion, scattering light in a way that favored one molecular hand over the other. The James Webb Space Telescope is now studying complex organics in star-forming regions like the Taurus Molecular Cloud and the Orion Nebula. JWST's infrared instruments have detected prebiotic compounds, including carbon chains and nitriles, forming under the influence of polarized starlight. These observations suggest that the chemical seeds of life naturally inherit directionality from their cosmic environment. When we ask whether the universe's spin decided the direction of life, the evidence points to a quiet yes. From the spin of galaxies to the handedness of neutrinos, from polarized light to chiral molecules, every scale of nature seems to prefer motion in one direction. It's as if life is not random at all, but a continuation of the universe's earliest rotation, written into every strand of DNA. As astrophysicist Carl Sagan once said, "We are made of star stuff. Perhaps we are also made of the spin of those stars, the angular memory of their light." Every cell inside us still carries that twist, a microscopic echo of the universe's turning. From the dance of galaxies to the spiral of our DNA, the same motion continues, smooth and silent, across billions of years. As we look deeper into that cosmic connection, another question emerges, not about beginnings but about endings. If everything that spins must one day slow, what happens when the universe itself forgets how to turn? Every rotation slows. Earth's days are getting longer. Galaxies are drifting apart, their graceful spirals losing momentum. Even the stars themselves, those furnaces of motion and fusion, are burning down one by one. The universe that began with a great spin seems slowly to be unwinding. But can motion truly vanish? Or does it simply fade, spreading thinner and thinner across the fabric of space? NASA physicist Michel Thaler stated, "Energy doesn't disappear, it disperses. So too with spin, it doesn't stop, it diffuses." Our planet, for instance, is already losing its rhythm. Each century, the moon's gravitational pull slows Earth's rotation by about 1.7 milliseconds, transferring energy outward. The result is that the moon drifts away by nearly 1.5 inches every year, a gentle dance that has lasted for billions of years. Laser reflectors left on the lunar surface by Apollo astronauts confirm this drift with millimeter precision. If this process continues, Earth's rotation will one day lock with the moon's orbit, each always showing the same face to the other, as the moon already does to us. It will be the end of tides as we know them, the end of the daily cycle of ocean and air. Planetary spin, once vibrant, will fade into equilibrium. Elsewhere in the solar system, the same story plays out. Mercury is already trapped in a 3:2 spin orbit resonance, rotating 3 times for every 2 orbits around the Sun. Venus, with its dense atmosphere, has slowed to an almost unearthly crawl, 1 rotation every 243 Earth days, and in the opposite direction of its orbit. Even Mars, whose day is only slightly longer than ours, is gradually losing speed. Over cosmic timescales, spin is not forever, it is a rhythm winding down. The slowing continues beyond planets into the heart of galaxies. Using the Hubble Space Telescope and Very Large Telescope, VLT, astronomers have measured the rotation of spiral galaxies billions of light-years away. When compared with modern galaxies, those ancient systems appear to have spun faster, tighter arms, denser cores, more angular momentum. As time passes, gravitational interactions and cosmic expansion gradually sap that motion. According to a 2020 study from the Leibniz Institute for Astrophysics Potsdam, galaxies may lose a portion of their spin through collisions and mergers. When two galaxies merge, their stars don't crash into each other, but their dark matter halos interact, redistributing angular momentum outward. This process leaves galaxies rounder, slower, and more diffuse, the spiral giving way to the ellipse. The European Space Agency's Gaia mission has mapped over 1.8 billion stars in the Milky Way, revealing that even our galaxy is evolving towards stillness. Its outer arms, once tightly wound, are gradually stretching. Over billions of years, friction with dark matter and nearby galaxies will drain its spin, softening its spiral form. Eventually, the Milky Way and Andromeda will collide, not in chaos, but in slow, silent fusion. Their combined rotation will settle into a single, massive, nearly motionless elliptical galaxy. But spin doesn't vanish when stars fade. It transforms. When a massive star dies, it collapses inward, conserving angular momentum and spinning faster than ever before. This creates neutron stars, city-sized objects that can rotate hundreds of times per second. NASA's NICER instrument aboard the International Space Station has observed pulsars spinning 716 times per second, their beams sweeping through space with the precision of atomic clocks. Yet even these cosmic lighthouses eventually slow, radiating away energy as gravitational waves and magnetic fields. As time expands further, rotation becomes scarce. Stars fade. Black holes, the last great engines of spin, slowly evaporate through Hawking radiation. In 1974, Stephen Hawking predicted that even black holes are not eternal. They leak energy and lose angular momentum over unimaginable timescales. A spinning black hole, known as a Kerr black hole, gradually transfers its rotation to surrounding space, leaving faint ripples of energy that stretch across the universe. ESA's LISA mission, planned for the 2030s, will detect these gravitational whispers, waves caused by spinning black holes merging and fading. Each detection will be a record of rotation being released into spacetime, echoing across billions of light-years. Even when the black holes themselves are gone, their rotational memory will remain imprinted in the geometry of the universe. Will the universe ever truly stop spinning? Not completely. Angular momentum cannot be destroyed, only spread thinner, shared among an ever-expanding sea of particles. As NASA explains, in an isolated system, angular momentum is conserved. The universe, in this sense, never stops moving, it only redistributes motion. Still, there may come an age when motion becomes imperceptible. In the far future, long after the last stars have died and galaxies have faded, the universe will enter what physicists call the heat death. Energy will be evenly distributed. There will be no temperature gradients, no flow, no reason for anything to move. Rotation will persist mathematically, but without contrast or structure, it will have no meaning. Some cosmologists, including Lawrence Krauss and Brian Greene, describe this as the cosmic silence, the final calm after every vibration, every orbit, every spin. In that distant epoch, protons themselves may decay, and black holes may fade into bursts of radiation. Only faint background photons and neutrinos will drift endlessly through space, carrying the last traces of the universe's once grand rotation. The James Webb Space Telescope peers deep into the past, but it also reminds us of the universe's future. Every ancient galaxy it observes is another tick backward on the cosmic clock, showing us how rotation once defined structure. In its images, we see both beginnings and endings, motion kindled by imbalance and motion fading into stillness. Even so, spin leaves fingerprints that cannot be erased. From the polarization of the cosmic microwave background to the curvature of spacetime around dying stars, the memory of motion remains encoded in the universe's design. It's not movement we lose, only the strength to notice it. Currently, Earth's core still turns. The stars still orbit, and the Milky Way still drifts through the darkness. Every motion we know is a flicker of that ancient rotation, one that will outlast us, but not eternity. When that eternity arrives, when the last spin finally stretches into silence, something else will still remain. Not movement, but the memory of movement. Because even when the universe forgets how to turn, its geometry will still remember that it once did. As we approach that horizon of stillness, another question quietly unfolds. If every atom, every planet, every galaxy is slowing down, what does that make us, the ones still moving within it? Every atom inside us is spinning. The electrons orbiting our nuclei, the protons and neutrons inside them, the quarks deep within, all are caught in ceaseless motion. That motion isn't random. It's a continuation, the faint echo of the universe's first rotation. When we move, when we breathe, when our hearts beat, we're not separate from the cosmos. We're part of its oldest memory, motion itself. In physics, angular momentum is the persistence of spin, the rule that keeps motion alive. It's why galaxies still turn, why planets still orbit, and why atoms still vibrate after 13.8 billion years. According to NASA's Goddard Space Flight Center, angular momentum cannot be destroyed, only transferred or shared. That means every spin in the universe, from the grandest to the smallest, is a continuation of the same original rotation that began at the Big Bang. In the beginning, the universe was not still. Measurements from ESA's Planck satellite show that the cosmic microwave background, the faint afterglow of the Big Bang, carries subtle anisotropies, slight directional differences in temperature. Some cosmologists interpret these as traces of the universe's first angular momentum, the original twist that set everything in motion. That primordial spin never vanished. It fragmented, spreading across scales from galaxies to atoms. When stars form, clouds of hydrogen and helium collapse under gravity. As they shrink, they rotate faster, conserving angular momentum like an ice skater pulling in her arms. This same rule gives rise to accretion disks around young stars, planetary systems, and even black holes. Each planet, each moon carries a fragment of that spin, embedded in its orbit. And within those planets, inside every rock, ocean, and living cell, the pattern continues at smaller scales. Our atoms too hold rotational memory. The electrons that define chemical bonds obey the quantum property of spin, a fundamental angular momentum intrinsic to all particles. This spin isn't literal spinning, but a quantum state, a value that determines how particles interact with magnetic fields. Without it, chemistry would not exist. NASA's Quantum Laboratory Initiative describes spin as the engine of atomic structure, the difference between chaos and stability. In this sense, every piece of matter carries an ancient choreography. The spin of particles leads to magnetic fields, which lead to structure, which leads to stars and planets, and ultimately to life. Our neurons fire using electrical potentials shaped by these same fields. Every thought that crosses our minds is an alignment of charged particles, a kind of ordered motion. When we ask whether consciousness might be the universe remembering its motion, the question isn't poetic, it's physical. Each brain wave, each signal is built upon rotations that have existed since the dawn of time. The magnetic fields generated by our neurons are faint echoes of the same electromagnetic principles that guide pulsars and magnetars. As astrophysicist Neil deGrasse Tyson said, "We are not in the universe. We are part of the universe, and the universe is in us." From a scientific view, memory is a form of pattern preservation, information encoded in physical states. Atoms remember through spin orientation. Cells remember through molecular structure. Stars remember through rotation curves, and the universe remembers through the geometry of spacetime itself. Einstein's general relativity teaches that energy and momentum shape spacetime's curvature. Every movement, every rotation leaves a small indentation, a swirl in the geometry of reality. This is known as frame dragging, confirmed by NASA's Gravity Probe B experiment in 2011. The probe measured how Earth's rotation subtly twists the surrounding spacetime, like a spoon stirring honey. Proved that spin isn't confined to objects, it extends into the very fabric of the cosmos. In a similar way, even our movements, though infinitesimal, also disturb spacetime ever so slightly. The difference is just scale. Our body's atoms spin billions of times per second, generating magnetic interactions measurable by quantum sensors. Each microrotation contributes to the ongoing record of motion that began long before humanity existed. If all motion leaves traces in spacetime, then perhaps what we call awareness is the way the universe perceives those traces through us, not as emotion or spirit, but as physical continuity, matter recognizing its own persistence. Consciousness, in this purely scientific sense, is a system's capacity to reflect its internal state. And that reflection is written in movement. Even light, the messenger of the cosmos, carries angular momentum. Photons possess spin 1, which determines how they polarize and interact with matter. Polarization patterns across the cosmic microwave background act as the oldest record of rotational memory in existence. ESA's Planck satellite and NASA's WMAP mission mapped these swirls in exquisite detail, showing faint B-mode patterns, signatures of primordial gravitational waves rippling from the universe's first motion. When we gaze at starlight, we're literally seeing the memory of spin. Light twisted and stretched by billions of years of motion. That light enters our eyes, triggers chemical reactions, and becomes part of our own neural motion. In that way, the universe doesn't just remember its spin, it continues to experience it through every observer it creates. Even as the cosmos expands and cools, these traces persist. Galaxies may slow, but their angular momentum never disappears. It's passed to intergalactic gas, to dark matter halos, to radiation. The JWST has detected faint filaments of gas stretching between ancient galaxies, structures shaped by those very transfers of spin. Every wisp of matter still moves to the rhythm set 13.8 billion years ago. When the last stars fade and motion becomes silence, those patterns, encoded in gravitational waves, particle spin, and frozen light, will still ripple faintly through empty space. They are not gone. They are written into the shape of everything that remains, like fossils of rotation forming the universe's deepest kind of memory. Motion preserved as geometry. Carl Sagan reflected, "The cosmos is within us. We are made of star stuff. We are a way for the universe to know itself." In the language of physics, that knowing is not mystical, it's through motion, energy, and spin. The universe continuously encodes and retrieves its own history. Every atom inside us continues to turn with the same spin that once ignited the first stars. We are a moving archive, a living part of the universe's ongoing memory. As we follow that idea that memory is movement, then perhaps what we call life is the brief moment when the universe pauses just long enough to notice it's still spinning. We began by asking why everything in the universe is spinning and why we feel completely still. We've journeyed through the physics of inertia, the birth of cosmic rotation, the role of spin in creating habitable worlds, and the way extreme rotation can bend time itself. We've discovered that spin controls time, that broken symmetry created motion, and that dark matter's invisible architecture holds spinning galaxies together. We've seen how the universe's rotation may have determined the molecular direction of life, and how all motion, from galaxies to atoms, gradually redistributes across cosmic time. What emerges from this exploration is a profound pattern. Rotation is not merely a property of the universe. It is fundamental to its existence. Without spin, there would be no structure, no time, no life. Motion creates meaning. From the quantum spin of electrons to the grand rotation of galactic superclusters, the same principles apply. Angular momentum is conserved. Energy transforms but never vanishes. And every rotation, no matter how small, connects to the original twist that occurred in the universe's first moments. We are not outside observers of this cosmic dance, we are participants. The atoms in our bodies carry the rotational memory of stellar furnaces. The rhythm of our days follows Earth's ancient spin. Our molecular structure reflects the handedness of a universe that chose one direction over another billions of years ago. Every heartbeat is synchronized to a planetary turn. Every thought arises from electron spins in neural pathways. Every breath we draw participates in atmospheric circulation shaped by the Coriolis effect. We are, in the most literal sense, made of spinning matter, and that matter has never stopped turning since the beginning of time. The paradox we began with, that we feel still despite moving through space at hundreds of thousands of miles per hour, is not a flaw in our perception but a testament to the universe's elegant consistency. We move together with everything around us in such perfect harmony that motion becomes invisible. This synchronized movement creates the stable platform upon which complexity, consciousness, and wonder can emerge. Our stillness is not the absence of motion but its perfection. Though all rotations gradually slow, motion itself endures. The universe may eventually reach a state where spin becomes imperceptible, spread so thin across such vast distances that it loses practical meaning. But the geometry of space-time will forever bear the imprint of every turn, every orbit, every spiral that ever was. In that sense, rotation is eternal, not in its intensity, but in its legacy. Perhaps the deepest mystery isn't why things spin, but why we exist at precisely this moment in cosmic history, when rotation is still vigorous enough to create stars, sustain planets, and give rise to minds capable of contemplating their own motion. We live in an era of dynamic equilibrium, when the universe retains enough angular momentum to be interesting, but not so much that it tears itself apart. We exist in the sweet spot of cosmic time, witnesses to a universe still actively spinning, still creating, still evolving. The universe that began with a twist continues turning through us. We are not separate from its motion, we are motion that has become aware of itself. Every rotation, from the subatomic to the cosmic, participates in a single, unbroken dance that spans 13.8 billion years. When we marvel at a spiral galaxy, trace the double helix of DNA, or simply feel the gentle alternation of day and night, we're experiencing different scales of the same fundamental phenomenon: the universe's inherent tendency to turn. Rotation is memory made physical. It is time made manifest. It is the universe's way of preserving its history in the very structure of space, matter, and motion. We are still spinning, always have been, and in that endless, gentle turn lies the secret of existence itself. That to move is to be, and to be is to participate in the grand rotation that will outlast us all, yet never truly end. The silence we perceive is not the absence of motion. It is the sound of everything moving together in perfect, eternal harmony.